Okay, so starting with Day 3, Part 2, and continuing through next week, we're going to take a look at several dynamic programming problems that you are very likely to encounter, at least some of these and very likely others, in your internship interviews. We're going to begin by taking a look at what's called the 0-1 knapsack problem. It's called the 0-1 knapsack problem because in your knapsack you can include either 0 of a particular item or 1 of a particular item. You're not allowed in this setup of the problem to use partial items. Okay. So in general, as a review, the methodology of dynamic programming is we want to find some solution to a complicated problem involving recursion on simpler subproblems. And our hope is that a lot of these simpler subproblems will be the same as each other so that we can do what's called memoizing solutions of simple subproblems that we've already accomplished and reuse those later to reduce what is probably an exponential problem, if we do it in a brute force recursive way, down to a polynomial problem. Okay, so usually when we're doing dynamic programming, we're going to have to be maximizing or minimizing something, and we will typically need to be making decisions along the way. So the same thing is going to be true here for our knapsack problem. All right, so let us imagine that we are going to go on a day hike down at Ohiopyle State Park, let's say, walk along the rail-to-trail thing they have down there and look at the Yakagani River. So we have a knapsack in which we're going to carry stuff that we need for our hike, and in there we can put items which are discrete items. Okay, so we don't have any partial items. For each one of these types of items, you can either include it or not include it. So if one of the possible items that we have is a flashlight, we're going to have to either include one of the flashlight or none of the flashlight. We can't do things like splitting our flashlight into pieces. Some of these items are not very heavy. Some of these items are quite heavy. Like a Coleman gas stove probably weighs about 20-25 pounds or so. You probably wouldn't want to carry that on a day hike. And for the formulation of this problem, we're going to assume that the weights of all these items can be specified as discrete weight units. All right, so we're not going to measure these things in pounds and ounces and fractions of ounces. We're going to just assign some integer value to represent the weight of each one of these items. And we're using an integer value so that we can build an array using those integer values as subscripts into the array. So right away this is a little bit artificial. But let's suppose that the sandwich that we might or might not the sandwich that we might or might not take on our hike is 1 unit of weight, and a bottle of water is 2 units of weight, and the flashlight perhaps is 3 units of weight. Our 22-pound Coleman stove, well, I think this is an overestimate, 88. I think I changed this somewhere along the way, but let's say it's 44 weight units if each weight unit is half a pound. In addition to having some weight that you have to carry, each item also has some value or some utility or benefit to you during your hike. Okay, so we're not going to be carrying this stuff around just for the heck of it. We want to carry a sandwich and a water bottle and a flashlight because they have some value to us. Now, unfortunately, we can't carry every conceivable thing. One of the whole big deals with going on hikes or going camping is figuring out what not to bring. Okay, so let's suppose as a constraint that your knapsack is only able to hold 15 pounds worth of stuff. Now, possibly you can carry more than 15 pounds worth of stuff if your life depends on it for a long distance, but here we're going on a hike that we want to have be a pleasant hike, and so we're going to limit ourselves to 15 pounds worth of stuff or 30 weight units worth of stuff for our hike, and we have to figure out how to maximize the value of the stuff that we're bringing subject to that constraint that everything has to be 30 weight units or less. Okay? Now, so the brute force approach here, which we can set up recursively, is to determine all of the possible subsets of items that we could take with us. Then, for each of those subsets of items, determine whether that subset weighs little enough that we can put it in our knapsack. And if it will fit in the knapsack, then we can compute the subset's value. If the subset won't fit in the knapsack, then it's going to have a value of 0 because we can't take that subset with us. And we're going to keep track of the maximum value over all of these possible subsets of items. All right, so this is a big problem in a literal sense. If we've got n items that we are considering carrying along with us, then we have to figure out how many subsets are there that just contain one item each, how many subsets are there that contain 2 items each, all the way up to how many subsets are there that contain n-1 items each, and then of course finally we have the one subset that consists of all of the items. All right, now that works out, and it's not hard to see this. It's the sum for the number of items going from 0 up to n of n choose k. That is, we have n items and we're choosing a subset of size k from that. N choose k is the number of possible combinations, the number of possible subsets that we can choose of a given size k, and that gives us this sum here, which you will almost certainly recognize. Another way that we can approach this problem to figure out how many subsets there are is to just realize, well, rather than actually computing each one of these possible subsets, let's just figure out how many there are. For each item, we can either include it or not include it. That is, we have a yes or no decision for each item. That means we have a yes or no decision for n items, which means that we have 2 to the n decisions that we can make, and so that is another way of computing the number of possible sets of items that we can take. All right, and it turns out, sure enough, by the binomial theorem, that this sum of all of the possible combinations of the various different sizes of sets is, in fact, 2 to the n. Well, that's exponential in the number of items, and of course, the whole purpose of dynamic programming is to try to find a polynomial solution to a problem whose brute force specification is exponential. So let's do better than that. All right, so if W is the total maximum weight that we're allowed to carry, then we're simply going to label the items from 1 through n, and we're going to assign a value to each of those n items. We also are going to determine the weight that each item currently has. Okay, so for the flashlight, maybe the value is 3. It's hard to measure the value of items that you're carrying in a knapsack on a hike to rank those in terms of dollars, but let's just arbitrarily assign 3 as the value of a flashlight. and we might assign, 10 as the value of a bottle of water. It's 3 times as important to us as a flashlight. And of course, each one of these things has a weights. Now, the order of these items, it turns out, isn't relevant at all. Now, if you watch or read various other presentations of this knapsack problem, a lot of people insist that you need to sort these items first, but that's not, it's not technically correct, and it's actually a bad idea, because sorting, as we know, is not free. Sorting the items is probably going to involve using an algorithm like quicksort or yes, what's the other one? Merge sort. I knew it started with an M. Okay, so it's probably going to involve doing something like a quicksort or a merge sort, and we know that both of those are order n log n algorithms, and we're actually hoping to do better than an n log n algorithm. We're hoping that we can find something that just is of order n rather than n log n. So you actually want to avoid sorting the items if you can, and in fact you don't need to do any sorting for this knapsack problem. Okay, now we're going to determine for each item whether we're going to put item sub I into our knapsack or not. And what we're intending to do is to maximize the value of all of the items that will fit into our knapsack. But to break this down to consider a single item at a time, let's just start with item 1 and say, okay, what we're really trying to do here is to compute the maximum of the maximum value if we do include item 1 in our knapsack, or the maximum value if we exclude item 1 from our knapsack. Okay, so that reduces the entire problem to just making a decision about item 1, and then recursively making that same kind of decision about each of the other items in turn. Now, we can be a little more specific about this maximum value if we include versus maximum value if we exclude. Let's suppose that we include item 1. Then the value of including item 1 is going to be the value of item 1 itself plus the maximum value of all of the remaining items in a reduced available size. Okay, the available size, the maximum amount of weight that we can carry is some number W. And so if we do include item 1, item 1's value is going to be the value of item sub 1. And the remaining available weight that we have for other items is going to be the total weight that we can carry minus the weight of item 1. All right, so if including item 1 and then doing this recursive handling of all of the other items, if that produces a larger value than not including item 1 and instead considering all of the other items fitting in the total W, then we know that we should include item 1. But if that value is lower than this maximum, we should exclude item 1. All right, so we do have a recursive formula that we can actually compute things with this formula, because we know we have assigned values to all of our items, and we know the weights of all of our items, and we know the maximum amount of weight that we're able to carry in our knapsack. This suggests that maybe we can get away with using a two-dimensional array in which we keep track of the maximum values as the rows, where we include just item 1, or where we include item 1 and possibly item 2, or where we include possibly item 1 and or 2 and or 3, and so on. And as the columns, we can use the remaining available weight that still exists within our knapsack. Okay, so let's turn this into a table. All right, so the columns are indexed with the remaining available weight that we have in the knapsack. And just because I can't draw a table with 31 columns in it, instead of a 15-pound knapsack with 30 weight units, we're just going to assume that we have 10 units of weight to illustrate what's going on here. So if we don't include any items at all, then the amount of weight is 0. Actually, I'm sorry, I said that upside down. Let me say that again. It may be after we include a certain number of items that we have 0 remaining weight available. Or it may be after we include a certain number of items that we have 1 remaining unit of weight available. And so forth. We might have 2 available units of weight remaining, or 3. And the most units of available weight that we would possibly have remaining is 10. That's the most amount of weight that we're able to put into our knapsack. Okay, and in our algorithm, we're just going to fill in each of the cells in this table. Now, if we decide to include item 1, again, let me rewind and say this in a different way. We're going to consider whether we should include item 1. And we're going to consider whether we can include item 1 and should include item 1 if we have no available weight remaining in our knapsack. Well, of course, if we have no remaining available weight in our knapsack, we can't include any items. So the value of not being able to include item 1 in a knapsack that can hold 0 weight, that's going to have a value of 0. So it turns out, in fact, that this entire first column is going to end up being zeros. If we have 1 unit of weight left, we can fill in a value here. Or if we can fit item 1 in our 1 unit of weight, we'll fill in a value here. But actually, to illustrate, on the left side here, we're specifying the weights and values of 5 items that we might be considering for inclusion. And it turns out that this first item, item number 1, weighs 3 units. So we're not going to be able to record any value if we only have 0 or 1 or 2 units of weight unused in our knapsack. It's only when we get to having 3 unused units of weight that we'll be able to fill in a value of 9 here. All right, now as we go through these rows, we're not considering the items independently of each other. We're considering the items as an increasing possible set of items. So for row 1, we're only considering, for each possible remaining weight that we have in our knapsack, whether item 1 should or should not be included in our knapsack. When we get to row 2, we have another item to consider. This is item sub 2, or item number 2, which has its own weight and value. But we're not ignoring item 1. So in row 2, we're considering what the maximum value is that we can obtain by using items from the set including 1 and 2. All right, so the subsets might be the empty set, or the set just containing item 1, or the set containing just item 2, or the set containing items 1 and 2. It sounds there like we're having this exponential explosion happening, But it turns out that we avoid that by being clever in filling out this table. And then similarly, when we get to the third row, what we're actually considering there is all of the combinations of items 1 and or 2 and or 3. All right, so let's walk through this. And by the way, each cell in this table is going to be the maximum achievable value that we can have for a given amount of available weight and a given subset of items. So we're going to start by just examining item 1, and by looking at the maximum value that we can get from item 1 given each of these possible available weights that we have in our knapsack. Now, if the available weight that we have in our knapsack is 0, then we can't include item 1 at all, and so the maximum value that we can have by using just, well, by excluding, I should say, by considering item 1. All right, so the maximum value that we can obtain by considering item 1, and in this case rejecting it, is 0 value. Okay, if we only have 0 weight units remaining in our knapsack, we can't include item 1, and so the value we have there is 0. The same thing is true for remaining available weights 1 and 2. All right, so this item weighs 3 units. If we have 0 units of remaining available weight, we can't include item 1 at all. That's obvious, I guess, because we don't have any items that don't weigh anything. If we only have 1 unit available weight remaining, well, something that weighs 3 units won't fit. So once again, that's going to give us a value of 0 as the maximum value that we can have for that, for considering just item 1 if we only have 1 weight unit available. Similarly, if we only have 2 weight units available, we cannot put item 1 in, and so the value is 0. When we get up to having 3 weight units available in our knapsack, now, because item 1 weighs 3 units, we can fit item 1 into our knapsack, and so the maximum achievable value that we can achieve by considering just item 1 in a knapsack that has 3 units of weight available is 9, the value of item 1. All right, so if we have 3 units of weight available in our knapsack, item 1 will fit, and the value of item 1 is 9. So that's the maximum achievable value. And it's probably obvious that because we're only considering item 1, and we're not considering any other items, that we're also going to get 9 as the maximum achievable value if our knapsack has 4 available units of weight remaining, or 5, or all the way up to 10. Okay, so if we have 4, 5, 6, 7, 8, 9, or 10 units of weight remaining available in our knapsack, the value, the maximum value that we can get by either including or excluding item 1 is 9, and that's the value that we get if we include item 1. Okay, so that is item 1. We've dealt with item 1. Now let's go on and see what happens if we consider item 2. Okay, so now we're considering item 2. Item 2 has a weight of 1 unit and a value of 7 units. But in addition to considering item 1, in addition to considering item 2, we must also consider item 1 along with this. But fortunately, we don't have to go back and handle all possible combinations, because we're seeking to determine the maximum value that we can achieve by including item 2 and or item 1. So if there is 0 remaining available space in our knapsack, as we saw with item 1, we're also not going to be able to have any positive value from considering item 2 either. Okay, so the value that we can get if our knapsack has no available space is 0 for item 2 as well. Now, for item 1, pardon me, I misspoke. For an available space of 1, let's see what happens. This is a little more, well, it is more complicated. Now we're going to actually do some work. All right, let's reason this out. So if I have 1 unit of available weight available in my knapsack, then item 2 will fit. What is the maximum value that I can get given 1 unit of available space left from including item 2 and or item 1? Well, it's going to be the maximum, as we said before, of the maximum that we got. Sorry, my pen is misbehaving. All right, so I got to get my pen working. All right. So it's going to be the maximum of the maximum that we had by not including item 2, and the maximum that we had by not including item 2 and only considering item 1 was 0. So 0 is one of the two possibilities. The other value that we have to consider is the maximum value of not including item sub 2, and that was 0, plus including item sub 2, which, sorry, I highlighted the wrong thing, which has a value of 7. Okay, so we're computing the maximum of 0 or 0 plus 7. All right, let me be clear why this is. Because this item weighs 1 unit. If we put that item into our knapsack, which has 1 unit of space available, the remaining available space for which we can consider item 1 is 0, okay? So column 1 minus the weight of item 2 gets us to column 0, and the maximum value that we could achieve by considering item 1 at that point was 0. So we're computing the maximum of 0 or of 7 plus 0. And of course 7 plus 0 gives me a 7. So the maximum value that I can achieve by considering items 1 and or 2, if I only have 1 unit of available space in my knapsack, is 7. All right, let's continue on with this approach. Now, moving on to if we have an available weight of 2, we end up having the same result, because if we have an available weight of 2, then we're computing the maximum of either the value of just including item, or just considering item 1, which was 0, or considering item 2 and the maximum value that we could get from item 1 with one less unit of available space. Okay, again, this item weighs 1 unit, so if we have 2 units available and we do include item 2 in our set, which weighs 1, that means that the contribution of item 1 is going to be whatever item 1's value is in just 1 unit of remaining space. Okay, so either this 0 or this 7 plus this 0. And of course that's 7, just like it was for having 1 unit of available remaining space. Continuing on. Now we're considering the case of having 3 units of available weight in our knapsack, and we're trying to decide whether we should include item 2 in that set and whether we should use 2's value 7 as the maximum achievable value that we can get from that. Well, now the situation is a little bit different because the value, if we have 3 available units of weight, of just using item 1 in our knapsack is 9, which is greater than the value of including item 2 in the knapsack. All right, so 9 is what we can get by just including item 1 in our knapsack. If we include item 2 in our knapsack, then what we can get is 7 plus 0. And 7 plus 0 is only 7. So in this case, we're not including item 2. We're only including item 1, and we have a value of 9. Okay, sorry about the dratted phone. Let's go on to the next position here. All right, so now we are looking at when we have 4 available weight units in our knapsack. Okay, and we have an opportunity now to use either item 2 and or item 1. Our choices are, in terms of maximizing the value, is either we can just stay with the value of 9 that we get by just using item 1, or we can compute the value of using item 2, which is 7, plus the value of using item 1, which is 9. Okay, so in this case, when we have 4 units of weight available for use in our knapsack, that's going to be enough space for both item 2 as well as item 1, and the value of those 2 items combined is 16 rather than just 9. All right. And at this point, now that we've used both item 1 and item 2 to give us a value of 16, starting from the place where we have 4 units of available space in our knapsack, that value of 16 is going to continue up through if we have an entirely empty knapsack that is able to contain 10 items of weight. All right, because in each case, 7 plus, well, let's move on to taking a look at 5. Okay, if we have 5 units of available weight in our knapsack, then 7 plus 9, that is the 7 that we get by using 1 unit of weight for item 2, plus the value of 9 that we get for using item 1, gets us to 16. All right, and that just continues. So 9 plus 7 is 16. This 9 plus 7 is 16, blah, blah, blah. Let's move on to taking a look at possibly using item 3 as well as item 1 and or 2 now. Okay, so we're going to consider item 3, and depending on the maximum value, we may use item 1 and or item 2 in addition to item 3. Again, starting at the left side of our table, if we have 0 remaining units of weight available in our knapsack, then we're not going to be able to store any of unit 3, regardless of its weight, and so we start with a 0 again in that column. Then we move on to the next column, in which we have 1 unit of available weight available in our knapsack. Now if we look at the size of item 3, well, it requires 12 units of weight in order to go into the knapsack. It's not going to fit in the knapsack if there's only 1 item of weight available. And in this case, we end up basically computing the maximum of the 7 from using items 1 and or 2, actually just using item 2, and the 0 that we can get by not using item 3, and the result there, of course, is 7. In effect, we've just copied down the 7 from the previous row, which just considers items 1 and or 2. In fact, this situation is going to continue for the entire remainder of this row. Okay, we can't include item 3 that requires 12 units of weight in our knapsack, regardless of what amount of storage we have available, because we only have a knapsack that will fit up to 10 units of weight. So we just fill in all the remaining items in that row with the values in the row above. Now, in this situation where you see a row whose maximum value entries are identical to the row above, that means that that item can't be used. And in this case, we clearly understand why. It can't be used because it's got a weight of 12, and our knapsack can only hold up to a weight of 10. So let's move on now to item 4. Okay, here we're up to item 4, whose weight is 5 and whose value is 3. If there is 0 remaining space in our knapsack, of course, we're going to get a 0 as the maximum value that we can have in the knapsack in that case. And now if we move on to having 1 unit of available space in our knapsack, we'll see that we still can't add item 4 that has this weight of 5, and consequently the maximum value that we can have considering items 1, 2, 3, and 4 is the same as what we can get just considering items 1, 2, and or 3. So we copy the 7 down in that case as well. That's going to follow through for the next 3 columns as well. All right, so if we have 2, 3, or 4 available units of weight left in our knapsack, we're still not going to be able to include item 4. So our maximum values are going to be the same as the maximum values just up through considering items 1 and or 2 and or 3. And so those 3 values, 7, 9, and 16, get copied down. We finally arrive at an interesting change when we get to column 5. That is, now we have 5 units of available storage in our knapsack, and we can use item 4 if we wish. Okay, now item 4 has a weight of 5, so it will fit into that available space of 5. But if we use item 4, there isn't any more remaining space. So the increment that we can get by also considering items 1 and or 2 and or 3 is this 0 over here from the 0 remaining available space. All right? So in other words, the maximum we can get here, if there are 5 units of available space in our knapsack, is going to be either the 16 that we already had by just considering items 1, 2, and 3, or 5 plus 0. Pardon me, 5 is the weight. 3 plus 0. So 3 is the value of item 4. And if we consider 3 plus 0, of course that's only 3. And so the maximum is going to be the 16 that we got from just considering items 1 and or 2 and or 3. Okay, continuing on. I hope that the pattern we've been following has become fairly clear, but let's formalize this with some notation that you could actually turn into code. We'll call our array A, okay, and the columns of A are the possible available space remaining in our knapsack. The rows of A represent the individual items, and the cells of A represent the maximum value that you can obtain by using items up to and including the item for that particular row, assuming you have the amount of space available shown in the column. If, here we're treating the available weight with this variable name x, if x minus the weight of the kth item, that is the current item that we're considering adding, if the available weight minus the weight of the current item is negative, then all we do is copy down the maximum value from the row above in the same column. Otherwise, if the available space minus the amount of space required by item k, or weight required by item k, is greater than or equal to 0, we can use that thing, x minus w sub k, as an index into the table. And now the maximum value for a particular cell in a table, such as column 5, row 4, is going to be the maximum of either the element above, okay, so it'll be the maximum of either the element above, which in this case was 16, or the value of the current item, which in this case was 3, plus the value of all of the prior items in the column where the weight has been reduced by the weight of the kth item. All right, so here we are in column 5. The item that we're adding takes a weight of 5. And so the column that we need to look at for getting the contribution from the prior items, 1, 2, 3, 1, 2, and or 3, is in the sub-0 column. Okay, because there's no remaining weight after we've included item 4. All right, so there's our formula that we're applying at each cell as we walk our way through. Continuing onward, when we get to column 6, meaning that there are 6 units of available weight that we can use now, we're okay. Let me back up here. All right, let's look at our formula. Okay, So, in other words, X is 6. So the available weight is 6. The weight of item sub 4 is 5. 6 minus 5 is greater than or equal to 0. That means we're going to have to compute the maximum of either the value above, that is this 16 above, okay, because that could be the maximum value if we're unable to use item 4, or it's going to be 3 plus the best we can do using the remaining available space, which is 1 unit of unused weight. Okay, so in other words, we're going to compute the maximum of 16, which is the value that we can get if we have 6 units of available space, just considering items 1 and or 2 and or 3, or 3 plus 7 is 10 if we do include item 4 and also accept the contribution from items 1 and or 2 and or 3. Well, once again, the maximum of 16 plus 10 in this case is 16, so we still end up with a 16. And if we move on to column 7, we see exactly the same situation. We end up with 16 in that column as well. So now let's move on to column 8. Here in column 8, we have 8 units of available weight in our knapsack. So we're going to compute the maximum of either the 16 that we can get by just considering items 1, 2, and or 3, or we're going to compute the value of item 4, which is 3, plus the value that we can get with the remaining 3 units of available weight from items 1, 2, and or 3. So now we've got 3 plus 9, which is 12. 16, the max of 16 and 12 is still 16. So we're as we move further to the right with our columns and we get more and more and more available space in our columns, the benefit of using item 4 plus the contributions of items 1, 2, and 3 is increasing, but still hasn't caught up with the 16 that we can get by just using items 1, 2, and 3 by themselves. All right. Now, if we look in column 9, finally, we get to a situation where we can get above 16. Okay, so if we have 9 units of available space in our knapsack, then when we compute k minus the weight of the current item, that's going to be 9 minus 5 is the weight of the current item, so that gives us 4. All right, so if we take the 3 units of value from item 4 and we add to that the 16 units of value that we can get by using items 1, 2, and or 3 in the remaining 4 locations, we finally get above 16. So now we've got a value of 3 plus 16, and that gets us 19. So we have finally gotten ourselves a value that's above 16. And then the same thing follows through for column 10. So if we have, or column sub 10, I should say. All right, so we can also achieve a maximum value of 19 for having 10 units of weight remaining in our knapsack and using some combination of item 4 and 3, 2, 1. All right, we're getting there. So we're almost there. Now we're just on to our next and final item. And without belaboring the point, here's our 0 that we get in the first column, the sub-0 column. Let me leave these equations up. And, whoops. Okay, so for an available weight of 1, the weight of item 5 is 2, so we still can't use item 5 yet. We just copy down the 7. For an available weight of 2, we can use item 2, we can use item 5, whose weight is 2, and the value of item 5 is 11. So 11 has item 5 has a small weight, a weight of 2, and a relatively high value of 11. So when we compute the maximum of either 7, the value above, or 11 plus 0, we see that the maximum that we can achieve there is 11 plus 0 is 11. Okay, so by using item 5, if we only have 2 items of available weight remaining, we can get a maximum score, a maximum value of 11. Continuing on with this, if we have 3 units of available space, then we can get 11 from item 5 plus 7 from the previous items to give us a maximum value of 18, which is certainly greater than 9. The same thing is true if we have 4 available items of space. We also end up computing an 18. And when we get to 5 units of available space, we're comparing 16 to 9 plus 11. So in other words, we were comparing 16 to 20, and now 20 is our maximum available value. Okay. In the next column, column 6, we get to, well, 16 here is the value that we could get, the maximum value that we could get by just considering items 1 through 4, some combination of items 1 through 4. And if we then add item 5, we can either get the 16 or we can get 11 plus 16 from items 1 through 4. And that gets us up to 27. If you follow, if you grind your way through these computations here, you'll see that 27 continues on for the remainder of the table. Well, goodness me, that took quite a bit of doing. But we finally got this bloody table filled. And the maximum that we can get for a knapsack that can contain 10 items of weight, given this collection of 5 items that we've arbitrarily labeled 1 through 5, the maximum value is 27. Okay, so the maximum value that we can get once we have wound our way through this algorithm, filling in all of the cells in this table, is a value of 27. Now, that tells us the maximum value that we could obtain, but it doesn't tell us directly which items were selected. There are various ways of figuring out what items were selected. One clever way, one interesting way, would be instead of just storing a numerical value in each one of these cells, you could store an object containing both the numerical value and the set of items that were used to create that value. And then as these values increase, the sets of items become the unions of the newly added item plus the previous collection of items. Okay, so that I will grant you is very hand wavy. It's kind of hand wavy on purpose, but I hope you can follow along with me and believe that that will work. Another way that we can do it, which is a little more brute force, but still effective, is we can just start from the lower left corner, which is the maximum achievable, and do a test to see whether that maximum achievable is greater than the value above it. Okay, since 27 that we get by using items 1 through 5 is greater than 19, which is the maximum that we can get for using items 1 through 4, that implies that in that final maximum, we must have used item 5, right? If we weren't able to use item 5, then the maximum value that we could achieve by using item 5 would have to be equal to the maximum value that we could achieve by using items 1 through 4. Okay, so because this value 27 is greater than the value in the previous row, that implies that we are using item 5. So the first step in our sort of brute force algorithm here is to start at the lower right, pardon me, start at the lower right corner and just look at the previous rows in that final column until you find the lowest indexed row that still has the same maximum value as is down in the lower right corner. All right, so in other words, if we saw 27, 27, 27 here, we would recognize that this uppermost 27, that must be the final item that we selected for our collection of items. In this case, the very last item does give us a maximum value that's greater than what we could get using the previous items. And so that means that we must have selected item 5. Now, moving on from there, we want to find the previous. How shall I say this? The next most previous. I'm not sure that's even English, but we want to find the previous item that is used based on the fact that we did use item 5. Okay, we did use item 5. Now, what item is the one that we used before we used item 5? Okay, so here, if we compare this value of 27 that we get for using items 1 through 5 to this value of 19, notice that we've already logically concluded that we must have used item 5. All right, we've already put item 5 in our list of selected items. Therefore, we can't also use item 4, because if we did use item 4 and we then used item 5, we would have to have a value of 11 increase moving from item 4 to item 5. Okay, whatever the maximum value that we had for item 4, if we're also using item 5, that maximum value has to be 11 greater than for the previous item that we selected. Okay, so we can reason that we did not use item 4 because 19 is not 11 less than 27. Now, we may have used item 3 based on this analysis, because 16 is exactly 11 less than 27. The problem here is the same as the original problem we talked about, which is that the value of all the items up to and including item sub 3 is no different from the value of the items up to and including item sub 2. All right, so from 27, which is our maximum value for all 5 items, we subtract 11 and we find the lowest row for which the value is 16, and that must also be another item that we have used. Okay, so we have used item 2 as well as item 5. And then continuing on with this same logic, notice that the value of item 2 is 7, so now we need to find the lowest row that has a value of 9, 16 minus 7. And that is item 1, so the last item that we must have selected is item 1. And in fact, now we can just add those up to see that this does give us 27. We get 9 plus 7 is 16 plus 11 is 27. And the sum of the weights, 3, 4, 5, 6, certainly fits comfortably within the maximum of 10 available units of weight that we have in our knapsack. Okay, so that is yet another way, in addition to using the idea of storing sets of items in the cells themselves. This is yet another way of determining which items you actually selected. Now, so we've run the knapsack algorithm. We have figured out what the maximum value is that we could possibly put into our knapsack. We have also figured out which particular items we selected in order to get that value, and we confirmed that that collection of items does have a low enough weight that it will fit. The last question to ask is, well, okay, so what is the performance of this algorithm anyway? We're hoping that we have got a polynomial algorithm for dealing with an exponential problem. Remember that we had, if we have k items, there are 2 to the k possible different sets of items that we would have had to check if we had checked them one by one. But here, by considering just item 1 in the first row and items 1 or 2 in the second, 1, 2, or 3 in the third, and so forth, we were able to reduce this to a rectangular problem from an exponential problem. But is this a polynomial solution? Well, what we have here is an algorithm where the performance is order of n, where n is the number of items, times w, where w is the number of different weight increments. Well, that seems nice. We've just got an n in there. We don't have an n squared or an n cubed or something like that. So can we claim this as a polynomial solution? No, because w, the number of different weights that we need to account for in this array, is an entirely independent parameter from n itself. W does not depend on n. All right, and so we can imagine as we get more and more and more granular with our weight resolutions, that even if n is some fixed value like 100, we could still have this algorithm blow up if w gets to be some huge number, like 1 million or whatever. This can become, well, I won't say unsolvable, but this problem can become too big to solve on your laptop, let's say, regardless of the value of n. All right, so this ends up being what's called a pseudo-polynomial algorithm. It isn't completely terrible as long as w is not ridiculously large, but it is not technically a polynomial performance in n itself. Alrighty, so I guess the key thing of all of this mess to remember is the equations that we looked at here about how to construct the array A and how to fill in the cells within that array A.